Uh, let's start our group meeting with, well, a special group meeting this time with Nicolas. Nicolas, could you share your screen, and thank you so much for your time to be with us.
Yes. No, thank you very much for your invitation. So let me see.
Yeah, it's boring when just one person's talking every week. So it's good to have outside people giving talks and lectures. So, and this topic is quite timely sensitive, so it's very important that you are with us today. So take your time, man. So it's about, usually our talks takes 30-40 minutes. If you want to go, it's not there is no strict restriction about it, the time. So if you go shorter or longer, it takes longer, that's fine. Okay?
Okay, thank you. Yeah.
All right, and everybody, sorry for interrupting. And Nicolas said in the very beginning that if you have any questions, perhaps now would be a time to turn off your microphone. But if you have a question, just turn on your microphone and shoot a question. So, all right, Nicolas, thanks.
Okay, thank you very much, Bernal, for the invitation, and thank you all of you guys for being here. So let's do it very informal, so please stop me at any point if you have any questions. So we'll talk about this idea of reconstructing non-standard cosmologies with dark matter. And this talk is basically based on this first paper done in collaboration with Paola Arias and Carlos Maldonado from Universidad de Santiago de Chile, and Alan Herrera, who was a student here and now he's in the US, I don't know where, doing the PhD. But it's also partially based on these two other papers, one made in collaboration with Katarina Cosme, with Maira, there in Canada, Thomas Cannon, and Ville Bastonen. Okay, so let's get started. So first, the usual slides about dark matter will be very fast because I think you guys are super convinced of the existence of dark matter. So just to point out a couple of things, is that we have several observations that indicate this existence of dark matter. Actually, it's a missing force and very different scales. So scales, kind of small scales, scales of few kiloparsecs, so rotation course, so scales of galaxies, so also scales of clusters of galaxies, and even higher scales, so actually the higher scales in the universe, so cosmic scales, with these anisotropies of the CMB that can be very well explained the framework of this lambda CDM, where dark matter, in particular cold dark matter, plays a fundamental role. So this map here corresponds to the measurement by Planck, and the most important part maybe on the top is this slide where they have an arepa, and if you guys haven't tried the arepa, you should try it. It's delicious. So in this 100% of these arepas, you know that 70% or so is in the form of dark energy, 5% is the normal matter, so the standard model basically, baryonic matter, and 25% of the arepa is dark matter, right? So now that we are convinced that arepa is the most delicious dish in the world, we can keep going. And so we are convinced that dark matter is there. However, we don't know exactly what it is. So we know basically that it's neutral, it's massive, or it's not massive, it's just massive. It is weak, so weak interacting is a very broad sense. I don't mean the weak interaction in the sense of the standard model. Just mean that the interactions are kind of weak enough, they are not very strong with the standard model. And that's not either completely stable or long-lived with the lifetime of the order of the scale of the lifetime of the universe or so. So we know that a particle with these properties has doesn't fit in the standard model. So dark matter needs new physics beyond the standard model, and that's why the study of dark matter is so exciting. That it's a proof that we need new physics beyond the standard model. Okay, so now the question is, how was the dark matter produced in the early universe? So there are many, but in particular we'll focus on the WIMP one, which is by far the most studied mechanism. So the idea of this WIMP dark matter is that in the early universe, dark matter was in thermal equilibrium with the standard model. In particular, in in chemical equilibrium. That means that if you want a couple of dark matter particles here, these black blobs can annihilate into a couple of standard bubble particles, and this reaction in equilibrium means that the interaction rate is the same the two standards. So we can have annihilation of dark matter particles, and the rate will be exactly the same as the annihilation of standard bubble particles into dark matter. So both the annihilation and the production happen in the same way and are exactly the same rate. That's the meaning of being in equilibrium. And in this plot here, I'm showing you the yield of basically the dark matter number density normalized by the entropy density as a function, if you want, of the inverse of the mass. So basically the dark matter mass over the temperature, the standard model temperature. And when dark matter is non-relativistic, you will see this characteristic decrease correspond basically to the Boltzmann suppression, right? So that's the equilibrium density. However, at some point we will break this equilibrium and due to the expansion rate of the universe. So at some point the expansion is so fast that particles will fall out of chemical equilibrium and they cannot annihilate anymore. So even if they could kinematically keep annihilating, they will just not meet, the collision will not happen, so the dark matter will not annihilate anymore, and we'll have a break in the equilibrium. The dark matter will fall out of equilibrium, and we will reach like a plateau correspond to dark matter relief density, which is produced in this WIMP mechanism. However, if a particle interacts very weakly, that means that the interaction will decouple earlier and have a relic abundance which is larger. And the opposite happens if a particle has stronger interaction, so we keep in equilibrium for longer and it will be much more diluted. So these three lines correspond to different interaction rates. So if you want different sigma v's, so thermally average annihilation cross section, and if you increase this sigma v, so the dark matter will keep in equilibrium, will be in equilibrium for longer, and then the dark matter relic abundance produced will be smaller. So this sigma v is one of the key parameters. Okay, and that's a paradigm of collisionless called WIMP dark matter. Right? Okay, I was telling you, so there are a couple of conditions that we have to have in order to make this WIMP mechanism, let's say, efficient. So one is that we have to have this cross section, this thermally average annihilation cross section, sigma times v, of the order of few times 10 to the minus 26 cubic centimeter per second. So that's the canonical number for WIMPs, right? For the masses, the WIMP mechanism is kind of independent on the dark matter mass. However, typically masses for WIMP dark matter is, say, in the ballpark of the GeVs or TeVs. And the other thing is that if we want to have annihilation cross section of order of 10 to the minus 26 cubic centimeter per second, what one typically needs is couplings of the order 1, say 1, 10 to the minus 1, 10 to the minus 2, or so. So order 1 coupling between the two sectors, between the dark matter and standard model. And one thing I want to emphasize is that this is completely independent of initial condition. And it's independent exactly because we reach equilibrium. And once equilibrium is reached, that means that we're losing all the information about the initial condition. For instance, the heating temperature, or the couplings of the inflaton with dark matter, or the standard model, or initial conditions, or the physics at super high temperatures. Okay, and for the dark matter, if you want to compute the dark matter relic abundance, what we have to deal is with this kind of Boltzmann equation, where n, as I told you before, is the dark matter number density, h is the Hubble expansion rate. This 3 here means that dark matter scales like dust. These are non-relativistic particles. So these 3 figures are important. And this right-hand side of the equation corresponds to the annihilation. So sigma v is the thermally average annihilation cross-section, n is the number density of dark matter, and nx is the equilibrium density. Right? So this is the kind of typical Boltzmann equation that one needs to solve in order to to keep track of the dark matter relic abundance. Okay, now the common law, as I told you before, is that if you want to have a WIMP, so this sigma v has to be of the order 10 to the minus 26 cubic centimeter per second. That's the standard WIMP. But actually, this has a very mild dependence on the mass. And here I'm showing you about the evolution of the sigma v as a function of mass. Well, it's not an evolution. It's really what's the cross section that you need in order to have the WIMP. So you can see this varies between, say, 2 and 4 or 5, if you want, 10 to the minus 26 cubic centimeter per second. And this correspondence is just because of the variation of the standard model degrees of freedom. Right? So this G or G star vary, they have a small dependence, and also this sigma v does depend on the mass, so that you can see it's a very small dependence. You always have to be in this ballpark of this 10 to the minus 26 for having the standard WIMP mechanism. However, if you have a model and you compute this sigma v, and it's much bigger than this 10 to the minus 26 or so, what you will produce is a dark matter under production. So you can say that your model is giving you only a small portion of the standard model, of the dark matter total abundance. So you can solve this saying that you have a multi-component dark matter, and say, for instance, that this cross-section is super big, so you're producing 20%, 1%, whatever, a small fraction of the total dark matter abundance. So as I told you, if sigma v is very high, you can always say that this dark matter or the dark matter of your model is only responsible for a fraction of the total dark matter abundance of the universe. So this multi-component idea of dark matter can solve your problem. However, if in a given model you compute the sigma v and you have a very small cross section, say sigma v much smaller than this 10 to the minus 26 cubic centimeters per second, you have a dark matter overproduction. And that's pretty bad, because then the universe is overclosed, right? So in principle, if you want to use standard cosmology, you're stuck at this point. However, and that's the point that I want to emphasize today, is that you can solve your problems using non-standard cosmologies. And I will define this non-standard cosmology in a couple of slides. So we'll focus on this scenario where, suppose you have a model, you take a parameter space in this model, you compute the sigma v, and it gives you a very small number, and small with respect to this canonical number, 10 to the minus 26 cubic centimeters per second, or so, right? Okay, so first, before talking about non-standard cosmology, let me define what's for me standard cosmology. So I put standard in this quotation mark because it's really, maybe it's just a prejudice. I mean, for instance, when you use the word standard in standard model, means that it has been tested to death, right? The standard model is standard in the sense that we're pretty sure that even if not the full theory, is at least an effective field theory of the whatever string theories or whatever. We know that all like competition of the standard model has to give the standard model as a low energy theory. However, when they use the word standard in standard cosmology, it really means the easiest cosmology that you can imagine. Because after all, we know what cosmology has to be. We know that the universe has to be dominated by radiation, but we know that has to be the case for energy smaller than, say, 1 MeV or something like this. We have basically no clue about what the cosmological evolution of the universe much before BDN. So at 1 MeV or so, or few MeVs, we know that the universe has to be dominated by standard model radiation, but however, at higher temperatures, we have no clue. So when we use the expression standard cosmology, what it really means is that we assume that the early universe was dominated by standard model radiation. And that's it. So it's standard in the sense that it's the easiest cosmological scenario ever, but also the most boring possible case, right? So again, standard cosmology for me means that the early universe was always dominated by standard model radiation, so that this standard model radiation is described by this equation, basically, where T is just the standard model temperature and G star is the effective number of degrees of freedom. So if the universe is dominated by standard model radiation, that means that the Hubble expansion rate is also given by this kind of expression. So Hubble expansion rate H is the square root, basically, of this energy density. Also in the standard cosmology, we assume that all the processes are adiabatic. That means that the entropy is conserved, and if the entropy density defined this way, so S is proportional to T cubed, that means that the temperature scales like 1 over A. A is the scale factor. So again, standard means energy dominated by standard model radiation and conservation of standard model entropy. That means that temperature always scales like 1 over A. Or two small variation of the relativistic degrees of freedom. Basically, T goes like 1 over A. And if this is standard cosmology, what non-standard cosmology means, okay, is any deviation from this paradigm. So, in particular, we will assume like a parametrization of this non-standard cosmology, assuming that the early universe was dominated at some point by a non-standard component, non-standard model component phi. So we assume that this field, whatever, phi, which at some point dominates the energy density of the universe. So, what's the characteristic of this phi? Well, I will not define it properly. It will be very generic. So, for instance, assume that it has an equation of state omega, so a random number. So, for all the analytics, I will take like a general equation of state omega, but for basically for all the plots, I will assume that it scales like matter, so like dust. So, I will take this omega to be 0. And the other characteristic of this guy phi is that it will decay at some point into standard model radiation. And that's basically it. That's it. So phi, this non-standard cosmology, is characterized by these two parameters at this point. It's a question of state, which for me will fix it to 0, and a decay width, because at some point this guy has to decay into standard model radiation, because after all, I want that at BDN, the radiation to be dominated, the energy budget of the universe to be dominated by radiation. So I want this guy to decay. So if I want track of the evolution of the energy densities, I have to solve this kind of Boltzmann equation, Boltzmann equation. The first one for phi, for the phi energy density, where now here I have 3 times 1 plus omega, which is because of the equation of state. Take a look at, if I take omega to be 0, this term becomes 3, as I expect for dust. And if omega is 1/3, is the question of state for radiation, this term here becomes 4. And it's what I expect for radiation. I have this term here minus gamma times rho, is because I want this phi to decay into standard model radiation. And this term here is exactly the same that I find here with a different sign. It's just because the phi is decaying into standard model radiation. So this will be like a source term for radiation. For the equation, the Boltzmann equation for radiation is, okay, this part, 4 because it's radiation, and plus gamma times rho phi is the energy that the standard model is winning when this guy phi is decaying into radiation. So I hope this is clear. And now the Hubble expansion rate will have a second contribution because of phi. So the expansion rate has 2 contributions. Actually, it has contribution of the that we have, and basically is phi and radiation. So for me, that's the parameterization with this non-standard cosmology. Okay, so just I want to be super picky, and actually this equation for radiation is not completely true if you take into account the variation of the relativistic degrees of freedom. If you assume that the degrees of freedom are constant, this equation is completely fine. However, if you take into account the variation of the relativistic degrees of freedom, you don't have to solve the equation for the for the radiation energy density, but you have to take Boltzmann equation for the standard model entropy density. It's okay, so this is the kind of equation that we want to solve. But as I tell you, I'm just here super picky. I need to solve this kind of equation only in the case where I want to keep track of the variation of the relativistic degrees of freedom. If not, this equation of the energy density is perfectly okay, perfectly fine. Okay, now I'm showing you the solution of these two sets of equations. So it's just the background, right? So here, the first plot on the left, I'm showing you the variation of rho as a function of the scale factor, but actually it's rho over 4. Why 8 over 4? Because I expect the radiation energy density to scale like 1 over the scale factor over 4, right? So, and these two curves correspond to the energy density of radiation, this gray dashed line, and the blue is the energy density of phi. Phi, I for the process assuming that it's non-specific matter, so it's basically dust. So that means that the equation of state is that if the equation of state is 0, rho has to scale like 1 over a cubed. If I multiply it by a to the 4, this just grows linearly. So its energy density is growing, if you want, and at some point decays. So that's why, so it's a forward law, and then it decays because I force it to decay into standard model radiation. And when I have the decay, I can see that I have a kind of increase of the of the radiation energy density, and that's why I see that at this point the standard model radiation is increasing, right? And it's increasing all just because the phi is decaying to radiation. So when phi decays into radiation, I'm pumping energy into the standard model, and the standard model radiation energy density is growing in this plot.
So,
right?
Nicolas, I have one question at this point. So far, there are only two assumptions. One is that the degrees of freedom is constant throughout the whole period, and the second is that this scalar just couples to standard model particles.
Right. Yes.
And it doesn't matter which ones, because at that time all of them are radiation anyway.
Exactly. Yes, that's why we are putting radiation. Yes. If they couple to say only to tops, whatever, they will thermalize very fast, and yes, you don't get exactly the details. Right. Yeah.
All right.
Okay, and now in this plot on the right, I'm showing the variation of the temperature as a function of the scale factor. So that is temperature times the scale factor. And why is this combination? Because I expect if the entropy is conserved, T times A has to be a constant, because T goes like 1 over A. So when this function is constant, when we have a plateau, that means that the standard model entropy density is conserved. So we see that before the decay and after the decay, the entropy is conserved. However, there's a point here when we have an increase or a relative increase of the standard model temperature, and it's because phi is decaying into radiation, it's pumping energy into the standard model, and we're just increasing the standard model entropy. Okay? This, now just mentioned, this was assuming that the relativistic number of degrees of freedom is constant. Now, if I make them vary, it's what you will see. So black line corresponds to the same as the gray dashed line, but now just take into account the relativistic, the variation of the relativistic number of degrees of freedom. It's basically the same information, but we have some bumps here, for instance, and here due to the variation of G star and G star S. But I mean, there's just details. All the other important physics is here. So that we have a variation or an entropy injection in the standard model because of the decay of phi, and also that at this point radiation energy density will not scale like 8 to the minus 4 as in the standard case. So there are 4 regimes I want to or 4 important scales. So one is what I call the quality. This first moment when the 2 energy densities are the same, right? In this part, the dominant is radiation. Here is phi, and this part, the quality is when they're exactly equal, right? Hence the name the quality. The moment where phi starts to decay is what I call end. So AN or TN is the end of the phi domination era. Basically, when the Hubble expansion rate is equal to the width. So it basically is this moment here when phi starts to decay. And the third scale, what they call critical scale, is where the phi starts efficiently to decay, or yes, and where the entropy is not conserved anymore. So one critical point is here when the quality is here when they are equal. The critical is here when we see this rise of rho standard model because of the effective decay of phi, and the third moment is more or less here, is when phi when it disappears, basically, when it decays completely, right? Okay.
Nicolas, I have a question.
Yes.
In this period in which phi dominates the energy, can an inflation period happen?
Sorry, I didn't understand the last part.
If a second inflationary period can happen in this phase.
Yes. Yes, completely. Okay? Not in this. Is the question of status is -1? You can have an inflation. Yes, I mean, but not in this case. Now we are assuming the question of state is 0, so in this case like matter, so there's no second inflationary era. But however, if you take this omega to be -1, like in the inflation, like for the inflaton, yes, you will have a second phase of inflation, right? Yes, thanks.
Okay, so in this case, do you have to worry about the number of folds if you change this folds number? Because there are bounds on this number, right?
Yes, but I cannot give you much information on that. Yes, I don't know if these numbers, this 60 number of e-folds that one will always have in mind, then I don't know. I don't know right now.
Okay.
Yeah, anyone will never take this omega to be -1 here. I will show you some plots with different the question of state, but never mind.
Okay.
Okay, so here I'm showing you the scaling of rho and of the temperature. So, in this first phase, this is flat. That means that A goes to the like A to the -4 before and much after the decay of phi. However, when phi is decay, when you have this growth here, the scaling of the thermal energy density is like A to the -3 half 1 plus 1. Where remember omega is the question of state of this phi. And also I'm showing you here the scaling of temperature. So much before and much after the decay of phi, entropy is conserved. So temperature scales like 1 over the scale factor. However, at this point where we have a very efficient entropy injection, T goes like A to the -3 over 8 times 1 plus omega. Right? This is just to show you some analytics that we will use in the future. Okay, now what happens when you take into account the dark matter? So what we have to do is not only to solve this third, which is the Boltzmann equation for dark matter, but we have to solve it in a specific background, and this background will be these two terms, so phi and the standard density. So what we have to do is simply, instead of solving one Boltzmann equation for dark matter, we have to solve this set of three Boltzmann equations, one for the phi energy density, one for the dark matter entropy density, and one for the dark matter number density, right? So these two have 5 free parameters. So for the particle physics or for the dark matter, we have the dark matter mass, as usual, and the dark matter radiation cross-section, sigma v, which we can take it to be a number, a pure number, not a function of the temperature, because after all, we care about the value of this sigma v at the moment of the dark matter freeze out. So we have two numbers for the particle physics, and for the cosmology, we have three numbers, three quantities, the equation of state, omega, that will take always to be 0, the temperature at which phi decays, and we want the temperature to be higher than 4 MeVs or so, because we don't want to mess up with BBN. And this parameter kappa, that is just the ratio of energy density, so phi over radiation at T equal the dark matter mass. If you want, this is the initial condition for the solution of the Boltzmann equation. So again, we have 5 free parameters, dark matter mass and sigma v for dark matter, and for cosmology we have the equation of state, which we fix to 0, the end, which is the moment at which phi is decaying, and kappa, which is just the ratio of energy density phi over radiation at T when the temperature is exactly the dark matter mass. Okay? So that's what we will solve numerically. So again, what is the question here? So we suppose that dark matter is discovered, right? And that we can reconstruct its particle physics properties. So suppose Zener, 1 ton, whatever, has some event, and this event points towards a dark matter mass of say 100 GeV, a Laplacian cross-section of blah blah picoband. With that, what you can do, you have your favorite model, 331, whatever, your favorite dark matter model. With that, you can extract the parameters of the Lagrangian, in particular with the mass you know, but for instance the coupling between the two sectors. And with that, you can compute the sigma v, right? And because you want to know, after all, how dark matter was produced. And what is that? If this sigma v is a gain of the order 10 to the minus 26, you say, okay, I not only discovered dark matter, but I'm pretty sure that dark matter was produced in the early universe by this standard WIMP mechanism. So you're fine, blah blah. However, if the sigma v that you get is super small, and again small compared to 10 to the minus 26 cubic centimeters per second, the standard WIMP mechanism fails. Because you say that the cross-section is very small, that means that the Rake abundance is super high, we're overclosing the universe, so the standard WIMP will not work. Well, it's kind of true in the standard cosmology. However, the question here is, can non-standard cosmology revive this WIMP paradigm? So even if I'm getting a super small cross-section, could this detection is be encompassed with the WIMP paradigm in some non-standard cosmologies? And if that is, we want to quantify, so what are the non-standard cosmologies that could make compatible this detection of dark matter with the WIMP mechanism? So that's exactly the question that I want to ask, to solve. So now this is, okay, suppose we have this kind of benchmark. So for the dark matter 1000 GeV, and the sigma v is 3 times 10 to the minus 28. So very small cross-section for the WIMP paradigm. What I'm showing you here is the parameter space that is compatible with, or can make compatible this cross-section with the WIMP paradigm. So this is a function of kappa. Remember, kappa is the ratio of energy density phi over the radiation when the temperature is the mass, the dark matter mass, and Tn is the temperature at which phi decays. So we want this to happen for temperature 4 MeVs or so in order to avoid problems with BDM. So that's why I don't want to be in this region. And I don't want to be in this region because in this region, the phi energy density is subdominant. So in this region, we have standard cosmology. And okay, and all this is for omega equal to 0. So what I'm telling you guys is that all these points along this blue line make this benchmark compatible with the WIMP mechanism. And what I want to do in the next is just convince you, or let's try to understand why exactly this shape, the shape of this.
So Nicolas,
so for doing that,
one thing. So,
yes.
So that region of in the bottom, rho phi smaller than rho r. So why exactly we don't want that? Because I mean, if it's if it's comparable to rho radiation, so what?
No, it's not that we don't want. It's that if this is the case, if rho phi is much more than rho r, the cosmology just the standard cosmology, because you have a phi which is subdominant, so it will make no difference whatsoever. So yes, if we want to avoid this, that we are sure that this region will not work.
I see, because you just back to what you had before.
Exactly, this is standard cosmology.
Mm-hmm.
So
I see.
There's nothing incorrect with that. It's just that we know that it will not work.
I see.
Okay. So in order to understand this plot, which is basically the final plot, I will put here these 3 lines, which correspond to the temperature of freeze out when T freeze out is exactly T equality. When T this one, this is right here, this it's like greenish, is when T freeze out is exactly T critical, and when T freeze out is equal to T end. Right? And I put 3 benchmark points here, 1, 2, and 3, and I will try to explain you what's physically happening in these regions. So the first case is when the freeze out happens at super high temperatures, much higher, for instance, the T equality. So here I'm showing you exactly the same plot as before. This green line corresponds to the equality, to this point where the 2 energy densities are the same. So I'm focusing on the case where the freeze out, when all the dark matter densities happen at super high temperatures, right? When the temperature is much higher than the equality. So the equality, the decay, and everything. So in that case, that's the by far the most studied case. So dark matter, okay, so this is a case where we have a late entropy injection. So in this case, the standard model density is dominated during the freeze out. So standard model density is dominant during the freeze out. So the whole expansion rate is dominated by standard model radiation. That's one point. And the entropy is conserved during freeze out. That means that T is K is like 1/8. So here I'm showing you the evolution of the yield. So as you can see, it's exactly as in the case of the standard case. So dark matter is following the equilibrium. At some point you have the freeze out, you have the plateau, and this guy will decay very late, right? And when you have the decay, you have a dilution because of the decay of phi. And that's happening when the freeze out happens at super high temperatures, and then these two processes, the dark matter production and the decay, happen at very different scales. So we can separate this process, and if you want to compute the final dark matter abundance, what you have to do is to compute the abundance in the standard case, and then take into account the dilution because of the decay, right? In the case where you have just a late entropy injection. So what you have to do is you compute, if you want, the yield in the usual case, and then you dilute it. And this dilution factor is, okay, so this part is exactly the result of the standard case that you can find in Coulomb order, and this piece here corresponds to the dilution. And you have the dilution, and you have this term that happens, so kappa, and Tn, and omega. So So it's very easy to compute this thing. So you can compute the yield in the usual way, and the dilution factor being due to the dilution, to the decay of phi, and that's it. So, and as I was telling you, this is the usual case where the two processes happen at very different stages. First, you have the freeze out, and when the freeze out is kind of finished, you have the plateau, and very late you have the decay, the dilution. That's the one case. A second case is when the T freeze out happens between T critical and T equality. So in this period here. So in this period you can see that the dominant energy density is phi. Yes, but phi is not decaying yet efficiently. So you can see that the entropy is still conserved. So T is still scaling like 1/8. So in this region, where if the freeze out happens in this region, is what they call case 2. So it's a case with a late entropy injection. In this case, phi is dominating the Hubble expansion rate. So that's what the main difference with case 1. So the Hubble expansion rate is not driven by standard radiation, but now by phi. But still the entropy is conserved because phi is not decaying very efficiently. So we have a late dark matter dilution when phi decays. However, when solving the Boltzmann equation, this Hubble expansion rate is not given by radiation, but by phi. Because phi, remember, is the one dominating the expansion rate of the universe. So when you solve the Boltzmann equation, you will have this kind of behavior. So the freeze out occurs basically in the same way. The main difference that happens in a universe dominated by phi and not by radiation. And then you have a dilution, right? However, the freeze out and the dilution happen not simultaneously, but kind of close. So you have to be careful when computing the final yield, because the final yield, will depend on, or if you want the freeze out, will depend on the characteristic of phi, because if the Hubble expansion rate is dominated by phi. So this piece here corresponds to the freeze out here, and you can see that it depends on kappa, for instance, and omega. So it depends on characteristics of the non-standard cosmology. And then you have the same dilution factor that appears previously. Okay, and now a third case is when the freeze out happens in this region, so between T critical and T end. And this case is very different as the previous one, because as you can see, the Hubble expansion rate will be dominated by phi, because phi here is much bigger than radiation. And also in that period, the entropy is not conserved. So in this period, phi is very efficient, it's decaying very efficiently in radiation. That means that entropy is not conserved because you have an entropy injection in the decay of phi. So this third case is very different, and indeed the freeze out and the decay, they happen kind of simultaneously, right? So the phi energy density is dominant during the freeze out. That means that the Hubble rate is dominated by phi and not by radiation. And also, I want to point out that the entropy in this case is not conserved in freeze out. So T doesn't scale like 1/the scale factor, but T will have this weird evolution that strongly depends on omega. So on the equation of state of phi. So that mass is diluted while producing, because the freeze out and the decay are happening kind of in the same period. So if you solve the Boltzmann equation, you will have this weird shape here, where we don't see a plateau. Before we have like a plateau and then a dilution. Here's the plateau and dilution, if you want, happen simultaneously. So when you have the freeze out, so when the dark matter yield starts to deviate from the equilibrium density, you will have that you will not have a plateau, but this shaped evolution, and then you reach the plateau. So this third case is funny because we have these two processes happen kind of simultaneously. And the very last case is when the freeze out happens very late, so the freeze out temperature is very small with respect to T end. So this case is we will not say that happens in a standard cosmology because as you see the cosmology is standard because the phi dominates at some point. However, it's happening so late that all the action happen in a universe which is efficiently, but if you want effectively, standard, say the cosmology is standard. Because even if the cosmology is non-standard, all the non-standard processes happen at very high temperatures, and the freeze out happen in a universe which is kind of standard in the sense that all the action happens at the very high scale. So in this case, in this scenario, as I told you, the freeze out effectively happen in a standard cosmology because all the non-standard processes happen at very high temperatures and they completely decouple from the freeze out. Yes, so the decay happened at very high temperatures when the dark matter was still in equilibrium when the standard model. So this is the kind of standard scenario. So that is a way of understanding this kind of plot. So these four regions. So remember, when the T freeze out is much bigger than T quality, when the freeze out happens between the quality and critical, these three is when the freeze out happens between T critical and T end, and this fourth scenario is never realized because we are taking super small cross section. So that was one example for a particular. So I don't know if you have questions at this moment. No. So what I show you was so what are the possible cosmologies that can make compatible this particular benchmark point with the WIMP mechanism. So 100 GeVs and this super small cross section, 3 × -28. But I have done the same exercise for different benchmark points. No, sorry, before that, let me show you what are the X freeze out, what the temperatures at which the freeze out happens. So this X is, remember, it's just the dark matter mass over the temperature. So we typically have this X for freeze out under 20 something for 100 GeVs. For this case of non-standard cosmology, we typically have a much earlier freeze out. So freeze out happen at X of order 18, 16, 14. So we typically have an early freeze out in this case of non-standard cosmologies. And now what I'm showing you here is I'm varying the particle physics. So for instance here, I'm fixing the cross-section but varying the masses. So if I vary the mass, and in particular if I decrease the dark matter mass, I'm exploring different corners of the parameter space. Right, so this is 1 TeV, 100 GeVs, and 10 GeVs for dark matter mass. And I do the same exercise, fixing the dark matter mass to 100 GeVs and varying the cross section. So here I change the units. So instead of cubic centimeter per second, I'm putting GeV -2. So this is equivalent. One can do the transformation. So again, if I'm decreasing the sigma b, so the cross section, I'm exploring higher values of kappa, so different regions of the parameter space. So the higher the kappa, the more non-standard it becomes, because kappa is a proxy of the relative importance of this phi energy density. We do the same varying the cosmologies in the sense of varying the equation of states. So before that was omega equal to 0, so here we put some crazy numbers, -2/3, -1/3, +2/5, just to see the impact on the parameter space when changing the equation of state of this guy. Right? But yeah. And here is like a very, at this point, a very academic exercise, but this plot will help us understanding next slide. So here, before what I was doing is what I was fixing. So I was assuming that the dark matter properties were understood, were discovered, if you want, and I was trying to test the cosmology. Which cosmology could make the WIMP paradigm compatible with my dark matter detection? Now it's just the opposite. I'm assuming that I know exactly what is the cosmology, and I am trying, and the question is, what are the dark matter properties that are compatible with my cosmology? This is completely fictitious. It makes no sense physically, but this will make sense in the next slide. So, for instance, in this plot here, in the upper left corner, I fixed the n to 7 times 10 to the minus 3 GeV, and kappa to be 10 to the minus 2. And the question is, what are the masses and sigma v's that are compatible with such a non-standard cosmology? And the question is all the points on this blue line, right? So if I take a dark matter of 1 TeV and sigma v of 10 to the minus 12, GeV minus 2, this is perfectly fine with the WIMP mechanism. Okay, and this black line corresponds to the standard cosmology. So if I'm here, so this 10 to the minus 9, GeV minus 2 is the same as this 10 to the minus 26 cubic centimeter per second. Sorry, I changed the units. But this black line corresponds to the standard cosmology, and this blue line corresponds to this non-standard cosmology.
So Nicolas, for instance, we could interpret these plots as the ratio between the blue curve and the black curve is the suppression in the abundance that one could have for a given dark matter mass.
Right.
For these cases where you have Tn some value and kappa another value and so on. Okay.
Exactly. Yes. So we did this for different regimes. So we call the benchmark 1, 2, and 3. So remember, this is not completely fictitious or physical exercise. We assume that the cosmology is perfectly known, meaning Tn and kappa, and the question was what particle physics parameters are compatible. So, for instance, dark matter of 1 TeV and sigma v 10 to the minus 12, but also dark matter of 10 GeV and sigma v of 10 to the minus 10, whatever. However, this exercise makes sense in this plot. So here is the same parameter space, so M and sigma v. And see again, this black thick line corresponds to the standard cosmology. So if cosmology is standard, the sigma v has to be of the order of 10 to the minus 9, GeV minus 2, which corresponds to this 10 to the minus 26 cubic centimeter per second. And that's what we know. If we want to have a WIMP with standard cosmology, no matter what the dark matter mass is, sigma v has to be more or less of this number, right? Now the question is, what are the masses and sigma v's compatible with the WIMP paradigm for a non-standard cosmology? And the answer is all these white parameter space. So if it's in this gray region, it is not this. For instance, if the dark matter mass is 1 GeV and sigma v is 10 to the minus 15, this is compatible with the WIMP paradigm, even if you change the cosmology. However, if you're in the white region, for instance, point here, if dark matter mass is 1 GeV and the sigma v is 10 to the minus 10, this plot is telling you that this is compatible. For which cosmology, you don't know. But at least it exists a cosmology that could make your WIMP mechanism viable. So again, all these, so in the standard cosmology, only this black line is compatible, right? Now, in non-standard cosmology, it's not only the black line, but also all the white region here. So, for instance, if dark matter is 1 TeV, the sigma v could span between 10 to the minus 9 to 10 to the minus more than 16, okay, 17 or whatever. So that's why this plot is interesting. This is really telling you that to which extent you can increase your particle physics parameter space. And for here, the only assumptions were that omega was 0, that dark matter was non-relativistic at the moment of the freeze out, so X freeze out higher than 3, and Tn was higher than 4 MeVs. That's it.
Mm-hmm. So
And,
that case would be a case
I
of
think that
would be a case of early matter domination, right?
Right, exactly. Yes.
And so, and in the previous slide, so those curves, yeah. So these points where you picked Tn, 10 to minus 3, 10 to minus 1, and 2, are they feasible?
Yes.
Yes, right. So it's okay.
Yeah.
All right.
Yeah.
Mm-hmm.
So if you want, what I'm doing for constructing this kind of plots, what I'm doing is taking all these curves, the blue curves, varying Tn and kappa, and all these blue lines will be in this white region.
Mm-hmm. Yeah, I see. Mm-hmm.
Yeah,
Because the requirement you have is that the Tn's should be larger than 4 MeV, right?
yes, and that matter to be recalled. So X freeze out higher than 3.
Okay. All right.
That's it.
Mm-hmm.
And I think that that's basically all that I want to tell you. Okay, yes, I have, this plot is super complicated, but, okay, this specific realization of all that I was telling you guys. So now it's dark matter, but in a particular model for the Singlet scalar dark matter. So in this case, dark matter, I think it's the simplest dark matter model ever. So dark matter is a real scalar that couples to the standard model via the Higgs portal. So here I'm plotting you the dark matter mass on the x-axis, and the y-axis is the Higgs portal. So basically the coupling between the Higgs and the dark matter. And in this black dashed line, this corresponds to the dark matter abundance in the case of standard cosmology. But if I modify the cosmology, so if I take Tn of 10 MeV, for instance, and this F is the same as kappa before, 10 to the 6. So instead of this line here, I can explore much smaller values of the Higgs portal and correspond to these black thick lines. So it's basically the same. So I'm saying that if I modify cosmology, I can explore values of the couplings, the two sectors, much smaller, and yes, and then I can evade some experimental bounds.
Okay. So.
Okay, two more things, just I'm kind of running out of time. So in all the plots I showed you before, for instance, all the, these plots here, there's always a degeneracy between two observables, because we have two observables, kappa and the end, and two parameters and a single observable, which is the Drake abundance. So we have two free parameters and one observable. If you want to break this degeneracy, we need another observable, another physical quantity. And for instance, primordial gravitational waves could be a key to know more about the expansion rate of the universe, because after all, the primordial gravitational waves that one can measure now have two basic inputs. One is the primordial tensor spectrum, if you want the inflationary tail, also the propagation, and the spectrum that one will measure depends on all the history of the expansion rate of the universe, in particular of what's the equation of state of the universe. So it's funny because we have these two studies that appear the very same week. So where one was trying to reconstruct so omega to the question of state at some point, and this Z, which is based in value kappa. So inventing like a possible signal and looking at what are the constraints that can be put by different gravitational waves experiments, like WBM, LISA, blah blah. Okay, I just want to be very briefly, and this brings me to the conclusion. So dark matter exists. The nature of dark matter is still unknown. I think we are very convinced. But understanding the property of dark matter is one of the major problems in particle and cosmology. So the WIMP paradigm is by far our favorite scenario, and we typically use the WIMP paradigm in a kind of standard cosmological scenario. However, we don't know much for the cosmology before BDN. So non-standard cosmologies are completely plausible, are very well motivated scenarios. So the expansion rate of the early universe will have driven by an extra component phi. This could be whatever, a heavy neutrino, any heavy particle which a long lifetime could do the job actually. So it's very easy to have non-standard cosmological phases of the universe. So this non-standard cosmology opens up the particle physics parameter space beyond the canonical sigma v of 10 to minus 26 cubic centimeters per second. And this non-standard cosmology with omega equal to 0, so dust, can make the WIMP mechanism viable for large regional parameter space if the dark matter mass is higher than 30 MeV or so. And if we want to break the degeneracy, we need other observables, for instance, these primordial gravitational waves. And that's it. Obrigado.
All right, thanks, man. So really good. So I'll give some space for the others to ask some questions. I still have one left. So does anyone have any question?
I have a question.
I have to.
You can make the question, Paul.
No, you start, please.
Okay. Nicolas, in this last slide, in this scenario, how can these gravitational waves be generated? What could be the source of these primordial gravitational waves?
Okay. Well, in this primordial gravitational wave, so the one coming from inflation.
Okay. The inflation itself. Okay. Okay, so the domination of this phi matter can shift the spectrum of this primordial gravitational waves from inflation. Okay, I see. All right.
Paulo?
Okay. Hi, Nicolas. Thanks for the great seminar. I'd like to know if, since this kind of WIMP you're talking about is more like feebly interacting particles, isn't it? What is the implication for the direct detection experiments? I think they have nothing to say about it, right?
Well, it's not a field, but still a WIMP because they really reach chemical equilibrium. It's true that the interaction rates are much smaller, but they are not that small. And they are not that small because we always wanted to reach equilibrium. So it's really a WIMP. And now for detection it depends on what it helps you invading constraints. That's good. It's bad on the other hand because it's much harder to test it. So for instance, in this plot here, it's it's complicated plot, but for instance, you can see that in this region corresponds to the part of the parameter space where it's excluded because of the invisible decay width of the tips. So in the standard case, this region, so if that matter is smaller than 60 or so, it's completely excluded. However, in the non-standard case, you can go up to, I don't know, this is 5-ish or so GVs. So it helps you because it makes all constraints looser. But it's also more complicated because it's more difficult to test these particles.
Okay. Another question, if I have time. What's the implication for the delta N effective? Is there anything you can say about it? Or is it completely agreed? Yeah, delta N effective.
Yes. No, it will make no difference whatsoever because they are. It's called dark matter. So
no, I see. No, it's called dark matter, but you putting another component to the early universe, which is the case in radiation, right?
Yes, that's right. But they want to decay early enough not to modify an effect. So I want to decay before BBM, so there are no constraints. Really, before BBM, you can do whatever you want with cosmology, basically.
Okay, so it has no implication at all to that one, delta NF.
Exactly.
Just one more. I don't know if you heard these last days, but people may be seeing some non-isotropy in the universe, or which may be related to the dark energy behaving differently in different directions. I know it's a new topic now, but do you have any idea how this could change this standard cosmology, mainly in the case of dark matter?
No.
Okay, it's just hot news, so probably you didn't have time to think about. Okay, thank you very much. Nice to see you again.
So Nicolas, okay. So just one last question. When you showed in one of the slides the change in, I think it was in the temperature or something, or rho, the density. When you do account for the degrees of freedom, the change in the degrees of freedom, and when you do not. Yeah, that one. So which degrees of freedom are you including? So this phi is coupling to the entire standard model spectrum, or just the fermions, or what?
No, if you want, it's exactly this. I'm just taking the variation of G star and G star S, so the relativity, the effective number of the freedom entering in the energy density and in the entropy. Mm-hmm. So it's exactly this.
Okay.
It's only this.
Mm-hmm. I see. So, and do you know how, for instance, if we have a UV complete model, how could we have this phi coupling to just the standard model spectrum and not dark matter? Let me see.
Yes, I forgot to say that. I'm kind of cheating here because the phi will couple. There's no way to avoid the coupling between phi and dark matter, because even suppose at the level of the Lagrange, if you make to couple or at 3 levels, the only direct coupling between phi and standard model. At loop level, you will have decay into dark matter via loops of standard model particles. So at loop level, it's impossible to avoid that. However, we really wanted to, we put this to 0 because we were lazy.
Okay, so at the end, maybe it will be just a rescaling in the weight of the scalar, right? So you just the branch ratio that will change a bit. I don't know. Because at the end, the results do depend on you assume the branch ratio of the phi into standard model to be 100, right?
Exactly.
Yeah. And if we change by 30%, how does that affect your results? Also by 30%?
That I don't know. I think we compute. So if the branching ratio is more than 10 to minus 4, I think we estimate that there will be no difference. However, if it's higher, yes, you can have some difference, but we just, I don't know what will be the impact.
Hey, can I ask a question?
Yeah.
So, this cap, so I was wondering about how can we understand, like, that plot of, let's say, sigma V versus dark matter mass? Yeah, so how can you learn from the lifetime of this of phi, like because the duration of this non-standard cosmology would be related to the dilution, right, of the production of entropy, and this will change the results. So can we learn something about the lifetime of this of phi that we need to? Yeah.
No, from this plot, no. This plot is only telling you whether you can or not make one point in the parameter space M sigma B compatible with the WIMP. It's not telling you at all which cosmology you need. It's only telling you that there exists a cosmology that could do the job for you.
So, okay, maybe not in that plot, but in the other, like this kappa is somehow related to the duration of the... Is like kappa and T end?
Yes.
Yeah, but
So
he's not specifying.
This variable is...
He's not saying, he's saying whatever non-standard I have will give you this suppression, that's all. So he's not saying whatever I can have is in this right region. He's not saying exactly what's the mass of the scalar or the decay of the scalar. He's just saying whatever I can have has to be within this white region.
Sure, but the dilution is related to the duration of the early matter or whatever.
Mm-hmm.
Yes, but then you have to care
to the lifetime.
Yes, but then remember you have to be careful because there are like different cases, and you don't know in which of them the freeze-out will happen. If the freeze-out happens here, or here.
Mm-hmm.
So what you have to do once you have like the particle physics parameter 6, so mass and sigma v, well, you have to solve these three Boltzmann equations, and you will have this kind of plots.
Mm-hmm. Okay, yeah. But did you try to relate with the amount of dilution you need? I think you are parameterized with this F parameter.
Yes, this capital D is the dilution, but this capital D is, I mean, you have to be careful, because for instance, the case depends on D. I mean, all the cosmology enters here in this dilution factor. However, in this case too, no. So this is the dilution factor, but also the initial abundance of this first plateau depends on the cosmology, because the freeze-out is happening when Hubble is dominated by 5. And in this third case, the dilution factor doesn't enter at all. I mean, it's not going to be well defined, because here the entropy is never conserved. So you cannot talk about a dilution due to the entropy injection, because the freeze-out is happening simultaneously as the decay.
I see.
So yes, the dilution factor, I don't think it's a good proxy of this.
Yes. Okay, thanks.
All right. So, further questions? No. So, thank you so much, Nicolas, again. And
thank you very much.
Yeah, thank you so much, everyone, for attending the talk. And we'll be finishing now. Bye. Have a good weekend.
Thank you very much. You too. See you guys.